Alright, so we have one circuit that we are going to build in experiment 6, and the circuit diagram for this is shown on page number, was that 11 of experiment 6 write-up. It's figure D-42 that we are going to build. And for this, we need a um, voltage source from a WaveGen, and it's a AC voltage source changing with time. And the voltage of that source, we are calling that as point A, denoting it as point A. There are four different points that are highlighted in red in this circuit. A is the voltage source, B is exactly the opposite of A, but now it is going to be digital, so it's going to be a binary signal. So it's going to be opposite or out of phase with respect to A, but it is going to sort of look square, like a square wave. C is going to be the voltage that you measure at the collector of the transistor Q1, and D is a voltage that you measure at the anode of the LED D1. And all those four voltage measurements are with respect to ground, of course. So your white, sorry, the orange stripe and the blue stripe wires should be connected to ground when we do this experiment. And as you might imagine, we only have two oscilloscope channels provided by the analog discovery, and we have four measurements to make here. So we are going to have to split it up as a pair-wise measurement. So we'll do AB and then AC and AD. So three different plots for this particular circuit diagram. So there are three different circuits, but they're all related. So in terms of building the circuit, they're all the same, but with slight changes. So we'll begin with the one that you see on your screen. Um, so it's a voltage source connected to 7414 1 kilo ohm resistor to the base of Q1. So let's start here. V1 is a voltage source, and I'm going to use the yellow wire from the analog discovery to provide that particular voltage waveform. So let's try to set that up in my waveforms window. So what I'll do is I'll go to WaveGen, turn that on, and right now it is a sinusoid waveform that I'm looking at. I need this to be a triangle waveform. The question is, how did I know it's a triangle waveform? Well, if you can see here, the rise time is half a second, the fall time is half a second, and the period is 1 second for this square wave or the pulse generator. So if you're generating a pulse, but the rise time is half a second and fall time is half a second, and that's your total time of 1 second pulse wave, then it is essentially a triangle wave, look, which should look like this, right? So half a second it rises, half a second it falls, and the total pulse width is 1 second. So it's essentially a triangle wave that we are trying to generate in this particular wavejet. So let's do a triangle selection, and because the period is 1 second, my frequency over here should be 1 over time period, which is going to be 1 hertz, and the amplitude is going to go between 0 and 3 volts. So if the amplitude is going between 0 and 3 volts, peak to peak is going to be 3, so which means I need to select an amplitude of 1.5 volts. And if you do a selection of 1.5 volts, it is going to be between negative 1.5 and 1.5. I need to offset that by another 1.5 volts. So I'm going to add that particular offset over here. Now it is going between 0 and 3 volts. Half a second it is rising and half a second it is falling, and the period is 1 second. So that is what I needed for WaveGen. So I set it up based on the pulse, V pulse that you would use in capture. Next, that is connected to the input of a 7414 IC. So on pin number 1, as you can see over here, back to the proto board view, the yellow wire from analog discovery is connected to pin number 1 of this particular 14 pin IC. The number on that chip should be 7414, suggesting that it's a Schmidt trigger based inverter. So hopefully we see two threshold levels for this. The output is on pin number 2 based on the circuit diagram. So there's a notch here which tells me what pin number 1 is, and in the counterclockwise direction I'm going to go 1 all the way to 7 and then 8 all the way to 14. It looks like we have audio issues. Do you guys have? It's fine on my end. The real circuit seems to be too small. You can actually make the smaller circuit into a bigger circuit. Let's see. Okay, let's come back to it. So this is the 7414 IC, 14 pin IC, and actually there is a schematic, right? You can look at all the details of how to use this chip if you look at the data sheet of that IC, but we have some information laid out in the experiment. So if you look at the view here for the experiment writer, 7414, it has 14 pins. Pin number 1 and 2 is what we are using for input and output. Pin number 7 should always be connected to ground, and we did that by connecting that's pin number 7 all the way to the right to ground, and we also connected pin number 14 to plus 5 volts, that's VCC. So if you want to use this chip to do anything at all, the first thing that we need to do is to provide the power and ground. After that, it is operational, and then you can use the 6 inverters that are inside it. We only need one of them, so we are just using pin 1 and 2. You could use 3, 4, 5, 6, and so on. So you have 6 options. We are just using the first one. All right, going down here to the circuit diagram. All right, so that's the chip 7414. That's right there. Pin number 2 of that chip is connected to a resistor R4. This is 1 kilo ohm, so brown, black, red. The other end of that resistor is connected to the base terminal of the transistor over here. So the center pin. The emitter, which is essentially the leftmost pin if you are facing the flat side, should be connected to ground based on the schematic. The emitter is connected to ground. The collector is connected to the negative side of the LED, the shorter lead. The longer lead is connected to the resistor R2, which is 510 ohms, and the other end of R2 is connected to voltage source V2, which is plus 5 volts. So that is how your circuit is built. I've connected the emitter to ground by using that black wire right there, and I've connected VCC to plus 5 volts using that, and I've connected R2 to plus 5 using that. So that's as far as building of the circuit goes. I've already set up my wave generator. So it should be technically ready for me. I'm going to plug in a few key things. For example, I'm going to connect orange stripe to ground and blue stripe to ground as well. Let's see, orange stripe comes out, goes to ground. Blue stripe goes to ground. Okay. Um, I also need orange and blue. So to start off, I will try to measure voltages at point A and B. So A is say on channel 1, so orange can go to A, which is also pin 1 of the 7414 chip, and the blue wire can go to the next pin or pin 2. So that should complete my circuit. Let's see, can I? All right, I might have changed something unintentionally, but questions about the circuit building. We are going to soon start looking at the waveform output. Okay, so now that I have all the connections, let's go back to the waveforms window, bring up supplies because I need plus 5 volts. So let's set this to plus 5 and turn it on. I actually don't need the negative supply, so I can turn it off. Just need the red one. And I hope you guys see that the light is, or LED is right now on. It's not blinking, but it is on. Let's also start our two oscilloscope channels. um, Run wavegen, run scope, and I hope you see that the LED is blinking very slowly because we have set the frequency to about 1 second, so you can see it very easily that it is blinking. But my waveforms window is doing a funny business, and the reason is by default the time base goes to 1 millisecond per division, which is looking at a very short time. So I'm going to increase this to about 1 second per division. That becomes too big. Maybe 200 milliseconds should do it. Okay, so that's good. I'm also going to change the offset so that uh, negative 1.5 and negative 1.5 for consistency. Okay, so that's let's also turn off noise. Turn off noise. Make the pulse width, plot width 3, say. That's my A and B. So points A and B. And what we would expect is this, right? A should have been measuring a triangle wave, which it is. The orange line is a triangle wave. B should have been an inverted version of A, but a binary signal. So it only has two levels, low, high, and it is inverted with respect to the triangle wave. So that's good. And it was a Schmidt trigger based inverter. So we expected this to have two thresholds. And if you can see, it switches from low to high at a much smaller voltage when you compare it with the input voltage that is needed to switch the output from high to low. So the output actually switches from low to high when the input is close to 1 volt, but it switches from high to low when the input is close to 1.5 volts. The specific details are uh, laid out in the plots that I uploaded on Piazza, so you can actually take a look at those numbers, the specific precise numbers over there. So that's AB. And then essentially what I would do is, if I wanted AC, I would move this blue pin and go to C, and I get that graph, and I would go to D at the very end, which is over here, and I would get that graph. I would need to adjust the offset a little bit to make sure that I'm able to see the entire thing. So the output is still switching low, high, but it is doing it when the input is close to here or close to here. So you still have two threshold levels, as you can see. Let us see what happens to this LED if you increase the speed. So let's go back to the WaveGen and make it 10 Hertz. I hope you see that the LED is now blinking faster, 10 times faster. Can I look at it when it is 20 Hertz? I can see it very comfortably that it is still blinking. In fact, if you go to 50 Hertz, then it kind of remains on. It appears as if it is on all the time, which is essentially the response of a human eye, which is why the refresh rate of television screens, the 60 Hertz number, is a standard. Because the human eye cannot uh, distinguish changes that happen faster than 40-50 hertz. So 60 hertz is pretty good. People who are gamers might be familiar with 120 hertz of a refresh rate, because that apparently makes it much more clear and smoother experience. So that's that come back to 1 hertz, and that's it. So those are your plots. So what I've done on Piazza is I took all these plots, AB, AC, AD, when this chip was 7414, and I swapped that out for 7404, which is a inverter, but it is a comparator, so only one threshold level. Similar operation, but just that it is not now going to switch from low to high, high to low only at one threshold level. I did that and I posted the results. And instead of looking at something that blinks, you can actually use a mechanical relay to hear something click. Unfortunately, I do not have a microphone that is good enough to pick up that very slight sound, but only I can hear it. It is very quiet, so it's very difficult to hear. I tried it in the morning. I couldn't get it to get the students to hear it. But the idea is, if you replace this LED on the right with a mechanical relay, and to protect the relay, you can put a diode in parallel with it. The mechanical relay works on a principle of electromagnet. So when current passes through a relay coil, it becomes a magnet and it is able to attract a metal plate that is nearby. So if you do that switching at a very fast rate, then you will hear a clicking sound. So I do have the relay with me, but unfortunately it doesn't give you any sound. So we are not going to do that. But I've already recorded the outputs of the relay 7404 chip, 7414 chip, and I've made them available on Piazza. All right, so now that's all I have planned for you guys for today. If you have any questions, please ask either by audio or by chat. Anything works. You can actually leave this to blink. What time are you posting the exam on Piazza this Friday, Wednesday? I will do that at 8 a.m. The LED is blinking because it changes between low and high. Yes, so it is blinking because sometime, actually for half a second, you are turning on Q1. When you turn on Q1, point C is connected to ground. When point C is connected to ground, that allows current to flow through the LED and it is on at that time. For the rest half of a second, when Q1 is off, then C is a dangling wire and the circuit is not complete, which means the current doesn't flow, which means diode LED it will be off. So that's why it's blinking, because we are selectively turning on and off the transistor, which either prevents current from flowing or stops allows current to flow through. Yeah, my cough gets better. Yes, sorry, it was better in the morning. For some reason, the cough. Uh, I don't know. Don't scare me. All right, let's see. 8 a.m. open for 8 hours. It actually opened for 9 hours. So until 5 p.m. When is drink? I am drinking water right here. When is the due date for experiment 6? Experiment 6 is due Thursday of next week. So we are looking at 2nd April. Sure. Do we still need to build the circuit? No. If you want to, if you have all the parts, actually you don't have all the parts. 510 ohm resistor, uh, you don't have that one. You may have the 1 kilo ohm resistor. Actually, you have everything except for the 510 ohm resistor. So you might be able to still do it. Um, here is a good trick. If you have multiple 1 kilo ohm resistors, you can put two of them in parallel, make a 500 ohm resistor, and use that instead. So yes, you have the ability to do this experiment. However, it's not required. So you just do it for your own learning. You don't have to do it. You don't need to do it. So just skip the building part. Uh, yeah, because um, in later experiments, it will become more of a challenge. So before the campus closed down, I spent about 4 hours trying to gather each and every component that I would use. So I have hooded my apartment with all components that I would need for the rest of the semester. The yellow line means, let me see, will the data for this part be posted on Piazza? Matt, it's already on Piazza. So if you look at resources page, there are 3 times 3, 9 plots that have already been uploaded on Piazza. Um, And so you just download those plots from there and pretend as if they were your plots and do the analysis. So there is still analysis to be done. There are still questions that you need to answer by reviewing the plots. But because I've done the experiment in front of you, you know what went on in the experiment, and you know how I collected that those results. The yellow line means voltage difference between A and B. No, the yellow line. I think you mean the orange line. The orange line is A. The blue line is B. Yes, orange is A and blue is B. Or in this case, it is D. Earlier it was B. So if you look at any of the plots, I have made a comment. So for example, over here, let's see, I have made a comment at the top of the plot saying which line corresponds to which color channel corresponds to which point. Okay. All right, other questions, guys? Drink some hot water. Yes, I will do that. I know it is annoying to you guys to listen me cough this much, and believe me, it's annoying me too. The good news is that um, there's nothing to worry. I'm gonna stop the recording now, and then I'll still be available for a few more minutes to answer questions.